And taking up the microphone now is Roger Meier from FCT ACTech Australia, who's going to talk about unlocking the new opportunities with X-series analyzers. A little bit about Roger. He's spoken here before, so maybe you remember him from his last presentation. He's been general manager of global business development at FCT ACTech since July 2020. He began his career as a product specialist in X-ray diffraction at Philips Analytical. Since then, Roger has gained more than 20 years of industry experience at industry-leading companies like FL Schmidt. Roger holds a diploma in mineralogy and a PhD in material science from the University of Erlangen in Germany. Another expert for us to take us through this next presentation. Over to you, Roger. We can see your slides, so I think you're ready to go.
Thank you very much, Thomas, for the kind introduction. Of course, I would like to change it a little bit now in a way that I don't focus on the high-end, let's say, science of the things. I would like to show you the real opportunities by using these analytical equipments. And this is also a pretty new approach these days to step from, let's say, headline analysis from an individual sample to continuous analysis in the world of XRD and XRF. We are well used to this already for the online analyzers based on nutrients and other radiation sources or moisture. But these days, I think in particular, this opportunity is great for the cement industry and opens a lot of opportunity to improve the efficiency, to reduce the CO2 emissions, and to get a very grip on the process. So in my talk, I would like to show you the general function of these online analyzers. I will go with you through 4 types of applications in the cement process. And of course, seeing is believing. I also would like to show you a little bit 2 cases where the raw mill analysis for certain cement plants can be a real added value to improve. And I will conclude my talk with a summary. FCT is already more than 25 years in the field of building these online analyzers. The origin of the company was a cooperation between CSIRO, Adelaide Brighton Cement, and FCT. And over the years, of course, we made all possible mistakes. But the good thing is we learned from these mistakes. And there we more or less in, let's say, 2015, 2016, my colleagues decided to make the ultimate online analyzer for XRD and XRF. And 3 main targets were to have a simple analyzer, to have as less as possible maintenance, to have it affordable, that the whole system is easy to be installed, and that it's very close to the sampling point. And we ended up with such a nice box like you see here on the right-hand side. For your information about the dimensions, it's about 75 by 50 by 60 centimeters. And it's usually located not more than 10 meters from the sampling point. Also based on this new technology, and in particular, the sample handling in the analyzer for fine powders with a particle size below 200 micron, we do not need any sample treatment or preparation. We can measure the powder directly, which gives you an extremely low time interval between sampling and the analytical results, which is a super precondition for you to do a successful process optimization and quality control. In case of coarser materials, there can be an inbuilt grinder or external grinder be used in the process, also to process materials like clinker. The system itself is self-containing, so it requires only a 1000 watt power connection. And we can report the results every 1, 2, 10, 20 minutes, depending on your needs and on the specific applications. Inside the system, the only thing which is moving is the sample material and the supporting equipment to move the sample through the analyzer. All the analytical components, they are in fixed positions. So we use semiconductor-based detectors, and this increases the reliability. Also, the systems, they come fully calibrated to you. That installation time is usually in the order of magnitude between 2 and 3 days, including a basic training. The whole equipment is or can be covered with a thing we call igloo. It's a ruggedization kit to protect it against mechanical attacks, heat, and moisture. And the system can be used mainly, the intention is to use it for online analysis, but of course, via the software, you can take it out of the automation and use it also as a backup for emergency for your lab equipment. Now, where do we see the analyzers? We see 4 crucial points in the cement manufacturing process, where the first point is the control of the raw mix color quality, and of course the influence via appropriate software. For example, the software we have seen before from Smith, the blend expert, to interact and to optimize the different feeders and to have a perfect raw mill. I always compare it like preparing bread. If you don't have the right ingredients, even after the oven, you will not get a proper bread. And therefore, this is one of the crucial steps in the production. At this point, we look only on the XRF part. If you go further down in the process, then you will see the next step could be the preheater. In the old days, the preheater was not there. Later, it was introduced. Nowadays, it's a very, very crucial step in the process because you reduce the energy consumption of the whole process by using a preheater, but it also can give you trouble. In particular, if you use a lot of alternative fuels or similar materials, then it can cause a clogging in the preheater. And if in the worst case, it can block the whole process, which will require a shutdown of the plant and cleaning of the specific parts, and you will lose a lot of production and money. And also the startup usually is not that smooth, so you want to avoid it. By using there a OFX or CMX analyzer from us, which is a combination of a XRD and a XRF machine. We use there a detection system for XRD, which is based on a strip detectors, and we use a XRF system with a silver tube and a solid state detector, which is energy dispersive, to measure also the element contents simultaneously. And there you get the whole information. You see the free lime content, which is the degree of calcination, which is important for the process control. But you can also detect critical elements like sulfur and chlorine, which can cause this clogging. And if you see these elements going up, you can proactively react on the process to avoid this trouble. Then, of course, after the kiln, when you have produced the clinker, you would like to check the clinker quality. And there again, the FLX or the OFX can do the job. These are instruments which can detect the halide concentration, the free lime content, plus in the case of the OFX, it will also cover the full elemental range from sodium to uranium. So you get a very good picture what is the quality of your semi-finished product at this point in the process. And the results, they can be either used for optimization of the pyro process or streamlining the next process steps downwards to the cement. And then the final instrument is placed after the cement mill. There you can either use an OFX or a CMX, which are very similar machines. Only the CMX has higher XRD capabilities. So you can measure more phases, like also this, you can determine the slag content, you can measure the fly ash, the sulfates, the clinker properties, etc. And this is for you the final step to be sure that the quality of the outgoing product is on target, but it can be also used to optimize the process steps before. So for example, if you switch between different qualities of cement, by analyzing the material coming out of the mill, you can switch between the different silos at the right point to avoid that you put too, let's say, costly cement in the low quality silo and vice versa, to avoid trouble and to optimize the production on the one hand side. On the other hand, you analyze the different compounds of your cement. which means this gives you the possibility to optimize the blending step. And by adding more limestone or more slag, automatically you reduce the clinker factor. Reducing the clinker factor will be very beneficial in the process, because either you reduce the energy and the CO2 emission, or you can use with the same resources, you can produce more cement. So there are different ways to utilize the results, and I'm very, very happy if you have specific questions to have a one-to-one discussion with you or with you and your colleagues to see what we can do for you. Now, in this talk, I would like to focus on the first application, the raw meal analysis, which we do with our RMX analyzer. As mentioned, it's XRF analyzer using a silver tube, where we usually measure the normal 8 elements like silicon, iron, aluminium, calcium, sulfur, magnesium, and so on. But of course, sodium, chlorine, and other elements are possible on demand, because we can cover the complete range of the elements which are accessible for the X-rays. The whole machine is fully automated, which means, and this is the big difference of our approach with all lab approaches, the materials goes into the analyzer directly from the sampler via this tube. And there we have sensors to steer the process of the sampling. And we have always fresh material in the analyzer. Then the material passes the analyzer, and after the measurement, it can leave the analyzer, either being returned to the process, or fractions of the sample can be also kept for further analysis in the lab or for other tests like the physical tests, etc. And this strategy gives you a very, very short time between sampling and the analysis. You get very frequent results, and it should be very easy to utilize the results. Usually what I do recommend is to use a software to do that, that you remove, as we heard also in the earlier talk, the human factor, that the quality and the processes are harmonized and they are not depending on the mood and the person of the day. So using this analyzer can be result in different benefits. By having a more, let's say, constant and consistent input into the kiln, you have a standard deviation of the LSF, which is much lower. And this will result, on the one hand, in lower fuel cost, because if you have a very good track on the LSF, you can optimize also the use of alternative fuels. And this can lead to a significant cost reduction in the process. We all know if we run a more homogeneous, constant process, we can reduce the energy requirements. But also when you produce your raw meal, many plants require a high quality limestone to correct the calcium content or other additives, which are usually much higher costs than the normal quarry material. By having a good track on the mixing of the material before it goes to the mill, you can also reduce the additive costs. And of course, if you have a very good homogeneous material going into the kiln, you will see that you have less wear and tear on the refractories in the kiln. So you can increase the lifetime of the whole equipment, and you will see that this will also on a long term remove the unplanned production steps. I know many plants, they have very, very, let's say, good homogenization silos, etc. But of course, they are also requiring a lot of energy. And it might be one option, if you measure more precise and more frequent your raw meal quality, that you can also save in these steps. At the end of the day, when the material comes out of the kiln, you will see, by having incoming material with very, very low LSF standard deviation, you can produce the clinker on target, which means the clinker must be not overburned, and therefore you can also save their energy in the cement milling. Also, the frequent characterization of the materials gives you this possibility to really go to the limits of using of alternative fuels. I only would like to bring into your mind that different fuels introduce a different amount of ashes into the process. So by knowing what is the fuel mix in the future of the day, you can more or less work more dynamically in the adaptations of the LSF. And at the end of the day, all these steps together, they bring down the downtime on the one hand, and on the other hand, they can also save a lot of lab equipment, which is usually more costly and more, let's say, maintenance intensive. Now, if we go into real cases, and I picked from the many installations we already have, one case of a cement plant in Europe, characteristics is they run one dry kiln with an average production of 700,000 tons per year. They work with two piles with an amount of 18,000 tons. And when they switched from, let's say, a classical lab and a neutron analyzers to our analyzer, the target was to reduce the LSF standard deviations. And here we see 2 1-month data sets of the LSF. The upper one is when they use the RMX, and the lower one before they use the RMX. Of course, you don't see so many points that you would expect in this period, because to really compare apples with apples, we decided to compare our results only in respect of the interval of the results they obtained in the lab, where they do one measurement every 3 or 4 hours. Because all the other measurements, they don't have the reference to the lab, and therefore we don't want to show them. We want to keep it simple, and we would like to compare apples with apples, because the lab results, they are usually the golden standard results. And if we look on this 1 month period, then we clearly see that the LSF standard deviation went down from 4.6 to 2.9%, which is really a significant improvement of the process. And if you carefully look here on the data sets, then you see periods like in this area here, where there is less deviations, and then there are these high swings in other areas. So I also extracted 1-week data sets, one in the smooth period, where you see a reduction from 2.5 to 1.8%, and one with more, let's say, deviations in the LSF, where the standard deviation went down from 7.1 to 4.5%. So you see, with this type of analyzers, it's good for optimizing the routine operation, but also for optimizing in more extreme cases. In this case, I assume that maybe it comes from end cone effects of the stockpile, etc., where you can also smoothen for these situations the composition of the material going into the kiln. And it's very, very clear by this significant reduction, which is down by almost 40% in the extreme cases, you get a lot of process benefits and quality benefits afterwards. So you see, with using the analyzer, of course, with a proper software in the background, you can reduce the LSF standard deviation. You will see smaller impacts of discontinuities like stockpile and cone effects. You can run feeder corrections more dynamic to adapt it for different situations in the process. This opens for you the possibility to use maybe more alternative fuels, and you produce more consistent clinker. Now switching to the second case, which is a cement plant in the US, and they already are very good equipped with 2 cross-belt analyzers and a robotic laboratory, but they were still not happy. And for that purpose, they decided to go for our equipment. And one of the, let's say, of the bottlenecks was the not too frequent sampling and sample analysis in the lab. So they wanted to have a more frequent results to adapt for different steps in the process, like the kiln carryover dust, etc. So here we see the installation itself. You see on the right picture, you see the air slide, and under the air slide there is a sampling system, and via this pipe the material goes directly here in a protected case, small container where our analyzer is installed. And more or less, how does it operate? And I forgot to mention that in the beginning. This is an analyzer which you usually don't switch on and off, because the analyzer gets the signals from the plant PLC. When material is running, the PLC takes care that the sampler is switched on. The material goes into the analyzer. The material is analyzed and then returned. And of course, we have this backup sample as well as an option. And more or less, the whole thing happens fully automatically. So there is no human interaction required. Also the start and stop by using the IOs from the sensors here. We have always fresh material in the analyzer. The analyzer will not run out of sample. Only when we get no signal from the plant PLC that material is flowing, then we empty the analyzer and then we more or less, we put it to the sleep mode. Now, if you look on the results and the impact on the process, you see here the black line in the middle of the diagram, where in the beginning they had no analyzer, and then we started with the analyzer. And this was really the first startup period, so there could be improvements still in the feedback loop for the different feeders, etc., because we see here some periodic oscillations. But you see immediately the big outliers and the big variations, they are gone by using these analyzers. Now, I mentioned before that it will also have impact on the clinker quality. And by using this setup, I can prove it that in certain cases, it will give you a lot of benefits. Because what you see that the clinker quality, and in this case, we specifically look on the halide concentration, reduced the variability. So more or less, we had before a standard deviation on the halide of 4.4, and after a more consistent raw mill, it went down to 3.6. And this also opened the possibility to increase the overall halide content in the clinker. So with this setup, and again, it was only based on the improvement of the characterization, so no other major changes were done at the plant, we could improve the halide concentration in the clinker from 60 to 64%. And this will directly, more or less, give you a lot of options to have benefits in the process. Because by higher halide, you can reduce the clinker factor by adding more limestone, more fly ash or slag or other additives. It gives you the possibility to reduce the fuel. It reduces the energy. And therefore, by reducing fuel, energy, and the clinker factor, you reduce also the CO2 emissions, which is one of the hot topics today. You can reduce the additive costs. You reduce the wear and tear by running the process more homogeneous. You may be able to reduce homogenization. There is a certain impact on the cement milling and on the clinker grinding. And one thing I didn't show you in this presentation because of time reasons, the analyzer can be, via the software, also taken out of the automation and be used for emergency cases as a backup of the lab equipment. And of course, the analyzer is so simple, so robust, that it requires only 20 minutes to 30 minutes maintenance per week. So it's much, much less than the more complicated automatic laboratories. It is the key tool to give you a consistent high quality clinker. You can use this to reduce the clinker factor, and you can use the results of the analyzer to increase the utilization of alternative fuels. And I, at the end, would like to thank you very much for your patience to listen to my talk. And I will try to answer all the questions. If I'm not able, here are my contact details. Please send us a mail and I will try to give you an answer to all the questions you have. Thank you very much.
Thank you very much, Roger. It's a really clear presentation outlining the benefits of this system. It's very compelling when you look at the operational benefits, and obviously trends going forward are for increased clinker substitution, increased alternative fuel utilization. So we can see very clearly the benefits of the lower LSF, which is the key target here. There are a few questions around I guess, comparing systems. One question relates to the US plant case where there was a cross-belt analyzer, and then you installed your XRF analyzer. And the question is, when you switched over, can you just describe that process? Did you close off one set of analyzers and then move over?
No, it's to make it very clear. Usually there are many plants that use two sets of analyzers.
Okay.
Cross-belt analyzer, and that's the cross-belt analyzer we don't intend to replace, is for the coarse material coming from the quarry. So there is no impact with our analyzer. But
okay.
if you look on the raw mill before the mill, then of course there are certain components missing because it's only added in or after the mill. And this is also the another question what I saw is that by placing the sampling point after the raw mill, you have the complete mix which will go into the kiln. So it's no assumption about how much bypass dust is added or other things. And by having this complete mix and a much better analytical quality of the data with XRF compared with the cross-belt, there you get this benefit.
So it's a kind of refinement and sophistication. You've got another level of control.
Yes, exactly.
That you wouldn't have had before. That's very clear. Questions around materials that you're analyzing. One about, again, coal. Is there an application for analysis of coal?
I don't have a proven concept for coal. I do know that in particular in South Africa, coal analysis is done quite often with XRD methods to see the different minerals in the coal, but also with XRF to see the overall carbon content. So for such applications, our analyzer would be very, very good. But of course, the main thing, which is my worry, is that we can handle the material in a proper way, because the analyzer is designed for fine, free-flowing material. And if his coal is in that type, that it's free-flowing and we can handle it mechanically, then I would be very happy to discuss what is possible for coal. But I don't have there a solution right from the drawer at this point.
Yeah. In terms of clinker analysis, is that the same issue in terms of handling it mechanically?
No, because for the clinker we have two options. Either we use a continuous disc mill before the material goes in, and that is something I did not show in the presentation. Usually, if you sample clinker, you need, based on the bigger particle size, you need a bigger volume. So usually, if you have a, let's say, average 20 millimeter clinker grains, you need to sample at least, let's say, 8 kilograms to be a little bit representative. Then the material is crushed, then transported via vibration feeder into the crusher, crushed, after the crusher, split, and then it goes through a continuous mill, and then the material leaving the mill is below 100 micron usually, and then it goes into our analyzer. So this is a complete, we call it a sampling tower to do the whole job.
Yeah, got it. Okay. And then I guess there's a question, maintenance, what kind of level of maintenance is required? I see that you contain it inside a kind of closed, encased box.
Yeah,
So
the box
quite
itself
protected.
is good for let's say for moderate moisture and the temperature range between -10 and +40 degrees. What I recommend is maybe to put a roof on top, or in southern countries to put a little bit a shack around it with a very basic aircon to be sure that the analyzer can run under these conditions. The weekly maintenance is maybe 20 minutes for experienced guy, and it's mainly a cleaning task and a checking task. Once per year we do the annual maintenance, so one of our specialists will come over to do this job. We do have a network of specialists globally, so there are people in Europe, there are people in Australia, in Asia, in India, etc. So we can cover the whole world.
Okay.
But for troubleshooting, we also have usually a remote connection to the analyzer, and 95% of all, let's say, tasks can be handled via remote. And also the analyzer is equipped with a camera that we see what's going on into the analyzer, and we record always the last pictures, that in case of an event that we can look back what was wrong. So was a coarse particle blocking the disk, or what happened? And then usually the main issue that happens in real life is that there are issues with the material feed to the analyzer, and usually not in the analyzer.
Very good. Okay, well, Roger, thank you very much. Roger from FCT, a really good presentation. Lots of interesting information. There's a few questions there you might want to look at, but for all of you watching who want this presentation, of course, you'll receive it by email after the webinar. So thank you very much, Roger.
Also, thanks a lot, and I appreciate to get the chance here. Thanks, bye.
Welcome. See you.